Welcome back to the Deep Dive. Today we are looking at, well, something truly cosmic in scale. Gamma ray bursts. GRBs. If you're trying to imagine the most powerful explosions out there, this is basically it.
Yeah, pretty much top of the list, second only to the Big Bang itself, really.
And the numbers are just hard to wrap your head around. I mean, a GRB can unleash as much energy in seconds as our sun does over its entire, 10 billion year life?
That's the scale we're talking about. It's absolutely immense, redefines powerful, doesn't it?
It really does. So our listeners send in some great material, and we're focusing on, I think, 3 key things people wonder about these.
Exactly. One, what's the actual risk to us here on Earth? Is it, Hollywood-level doom or something else?
Right. 2, do we have any kind of shield, any defense at all?
Mm-hmm.
And 3, can we see one coming? Do we get a heads up?
Okay, let's dive into that. The physics first. How do you even generate that kind of energy? Peak power, like all the galaxies in the universe, combined. What is happening? So for the long-duration GRBs, the ones that last more than a couple of seconds and pose the main threat, it's usually from the death of truly massive stars.
Like how massive?
We're talking maybe 20, 30 times the mass of our sun, or even more. They go hypernova.
Hypernova, okay.
And as the core collapses, it forms a black hole. But here's the crucial part the sources emphasize. The explosion isn't like a big sphere going outwards equally in all directions.
Yeah, right. It's focused.
Exactly. The energy gets channeled. It follows the star's rotation axis, forming these 2 incredibly narrow beams.
Jets, the lighthouse effect people talk about.
That's the one. And it's that focusing that thankfully protects us most of the time.
Okay, so these beams, these relativistic jets, what does relativistic actually mean here? What's in the beam?
It means the stuff in the jets, mostly plasma, superheated gas, tangled magnetic fields, is shot out at speeds incredibly close to the speed of light, almost at light speed.
Wow.
And it's these focused streams of energy hitting surrounding material that creates that incredibly bright, short flash of gamma rays we detect.
So, because space is vast and these beams are narrow, our safety basically comes down to luck. Cosmic geometry.
Pretty much, yeah. Natural cosmic geometry. The odds are just vastly stacked against one happening nearby and being pointed directly at us.
But if one were aimed right at us, how close would it need to be for, actual catastrophe?
That's where distance becomes our shield. The research suggests the danger zone for really catastrophic mass extinction level effects.
Like wiping out most species.
Yeah, that kind of level is somewhere between 5,000 and 8,000 light years away. And it has to be aimed right at us.
Which 5,000 light years sounds far, but in galactic terms.
It's practically our backyard. The Milky Way is about 100,000 light years across. So yeah, 5,000 is relatively close.
And the sources mention an even scarier threshold, something about 200 light years.
Right. If one went off within, say, 200 light years and was pointed at us, the beam's intensity could be enough to potentially just vaporize the atmosphere on the side facing it.
Vaporize it. Okay, that's unthinkable.
It's an extreme scenario, requires incredibly bad luck. But the physics allows for it.
Okay, let's pivot to defenses. If one is headed our way within that danger zone, does Earth have any natural protection?
The atmosphere. Magnetosphere.
Well, this is interesting. The magnetosphere, which protects us from charged particles like the solar wind, it doesn't do much against gamma rays themselves. They're high-energy light photons.
Ah, okay, so it's the wrong kind of shield for this threat.
Exactly. But the atmosphere, our thick blanket of air, that's actually incredibly effective at stopping those initial gamma rays and X-rays.
So the blast itself, the immediate seconds, might not be that bad on the ground.
Correct. During that short initial burst, the atmosphere absorbs almost all that high-energy radiation. If a GRB hit us from, say, 6,000 light years away, you probably wouldn't notice the flash itself down here on the surface. It'd be over in moments.
Okay, that sounds surprising. Okay, so if the initial blast is absorbed, what's the real danger the sources talk about? There's a catch, right? There is, and this is the crucial part. The danger isn't the immediate impact. It's the slow burn chemical fallout in the atmosphere after the burst.
Chemical fallout? How?
When those super high-energy gamma rays slam into the upper atmosphere, they don't just get stopped. They have enough energy to literally break apart the nitrogen and oxygen molecules, N2 and O2.
They shatter them.
Yeah, they rip them apart. And the fragments reform into different molecules, specifically huge amounts of nitrogen oxides, things like NO, NO2.
Nitrogen oxides, like smog, but way worse.
Much, much worse, and on a global scale. These nitrogen oxides are incredibly efficient at destroying ozone, the O3 molecules that make up our protective ozone layer.
Oh, so the GRB basically triggers a chemical weapon against our own ozone shield.
That's a good way to put it. These nitrogen oxides act like catalysts. They aren't used up in the reaction, they just keep breaking down ozone back into regular oxygen, O2, over and over again.
For how long?
The models suggest this chemical assault would lead to a rapid global drop in ozone levels, maybe 25 to 35% on average.
Global.
Yes. And in some regions, the depletion could be much worse, perhaps up to 75% locally. And crucially, this isn't a short-term blip. The ozone layer would stay damaged for years, maybe even a decade or more.
Wow. Okay, so the consequence of that is suddenly the Earth's surface is exposed.
Exposed to deadly levels of ultraviolet radiation from the sun. Unfiltered UV. That's the actual mass extinction mechanism.
Because the ozone layer is what normally blocks most of the harmful UVB and UVC.
Exactly. With the ozone layer significantly depleted for years, the UV index at the surface would skyrocket. The sources mention it could cause something like 16 times the normal rate of DNA damage.
16 times? That's unimaginable. Forget sunburn.
It's sterilization.
Yeah.
Especially for surface life. Think about marine plankton, the base of the ocean food web. They live near the surface. They'd be wiped out.
And terrestrial plants.
No.
Crops.
Devastated. Photosynthesis would collapse globally. It leads to a cascade effect through the entire food chain. It wouldn't matter if you built a bunker to survive the initial, non-event. The environment afterwards would be hostile for years.
And this isn't just theory, is it? There's speculation this actually happened in Earth's past.
There is. A leading hypothesis for the late Ordovician mass extinction, about 450 million years ago.
One of the big 5 extinctions.
Right. Wiped out something like 2/3 of all marine species back then. The pattern of extinction seems to fit what a GRB aftermath would cause.
How so?
Well, the sources point out that species living in shallow water, like certain types of trilobites, were hit much harder than species living in deep water.
Ah, because the water itself would offer some UV protection.
Exactly. The deeper you go, the more UV gets absorbed by the water. So creatures living deep down would have been shielded from the worst of that surface UV spike, while shallow water life got fried. It matches the expected pattern.
That's sobering. It connects this abstract cosmic event directly to Earth's history. Okay, that brings us to the third big question. Detection and warning. How often do we actually see these things?
Well, we see them surprisingly often, technically speaking. Our high-energy space telescopes, satellites like Fermi, Swift, previously BASI, they scan the skies constantly.
And they find them.
They detect, on average, about 1 GRB per day.
1 per day? That sounds frequent.
It does, but here's the key. Every single one of those detected bursts has originated from incredibly distant galaxies, billions of light years away.
Okay, so cosmically distant, therefore harmless to us.
They're completely harmless. They're just too far away. We see so many because we're looking out across a huge volume of the universe where stars are constantly being born and dying in billions of galaxies.
So the actual rate of one happening within our own Milky Way galaxy, that's much rarer.
Much, much rarer. The estimates vary, but the sources suggest maybe one powerful, long-duration GRB happens in a galaxy like ours only every 10,000 years to perhaps every million years.
Okay, that's a big range, but definitely rare.
Very rare. And then you have to factor in the narrowness of the beam, the lighthouse effect again. Only a tiny fraction of those rare Milky Way GRBs would happen to be pointed directly at Earth.
So the odds are low. But let's talk warning. If one did happen nearby, say 5,000 light years away, aimed right at us, would we know it's coming? Any advance notice at all?
This is probably the starkest finding in the research. Absolutely zero warning. None.
Zero? Why not? Don't we see the star about to explode or something?
The problem is the signal itself. Gamma rays are light. They travel at the speed of light, the ultimate speed limit, so the burst radiation arrives at exactly the same time as any visual light from the event itself.
So if it's aimed at us...
You wouldn't see it coming, literally.
Yeah.
1 second, things are normal.
Yeah.
The next second, the gamma ray wave washes over Earth. There's no precursor signal traveling faster than light to warn us.
Didn't we get a tiny warning with that neutron star merger event a few years back, the gravitational waves?
Ah, yes, GRB 118E08 118A. That was a breakthrough. We detected the gravitational waves from the merging neutron stars first.
How much warning did that give?
About 1.7 seconds. The gravitational waves arrived just 1.7 seconds before the gamma ray flash.
Okay, so scientifically amazing, but practically useless for any kind of warning or defense.
Exactly. Functionally instantaneous over cosmic distances.
So when astronomers get excited about detecting a GRB and swinging telescopes around, what are they actually looking at if the main burst is already over?
They're looking for the afterglow. The initial gamma ray flash itself might only last milliseconds to, say, a minute or two. It's incredibly brief.
Right.
But that intense blast of energy slams into the gas and dust surrounding the dying star, creating a massive shockwave. And that shockwave heats up the material and makes it glow across the electromagnetic spectrum.
Ah, so a lingering effect.
Yes, a much longer-lasting, lower-energy afterglow. We see it in X-rays, visible light, even radio waves. This afterglow can linger for hours, days, sometimes even weeks.
And satellites like Swift are designed to catch that.
Precisely. Swift detects the initial gamma ray flash, figures out a rough position, and then this is the clever part, it can automatically and very rapidly slew, meaning pivot itself, to point its X-ray and optical telescopes at that spot to catch the fading afterglow.
Why is studying the afterglow so important, then, if the danger is past?
Because the afterglow tells us everything. Its spectrum and how it fades tells us about the explosion's energy, the environment around the star, the type of star that exploded, and crucially, it lets us pinpoint the exact location.
So you can figure out which galaxy it came from.
Exactly. We can measure its distance, study its host galaxy. Yeah. It unlocks the physics behind the burst. It's all about rapid science, not planetary defense. There's no defense against the burst itself.
Right. Okay, so let's pull this together. Final assessment time. Given the rarity within our galaxy, the narrow beams, the distance needed, what's the bottom line? Are we safe right now?
Well, the scientific consensus seems to be probably safe. It relies entirely on those natural factors we've discussed, distance and the sheer unlikelihood of being in the beam's path.
No nearby candidates ready to pop.
As far as we know, there aren't any stars within that few thousand light-year critical danger zone that look like they're about to undergo this specific kind of core collapse and produce a GRB aimed at us anytime soon. So the immediate neighborhood looks clear.
But if that luck did run out, if a nearby star targeted us, what could humanity actually do? Is there any mitigation possible? Deep bunkers, lead shields.
This is the sobering part. For a direct hit from a nearby GRB, the sources are pretty clear. There's essentially nothing we could do to protect civilization as a whole.
Nothing.
Nothing effective. The radiation arrives instantly. And the main threat, the atmospheric destruction, the years of lethal UV, happens on a planetary scale. You can't build a shield for the entire ozone layer. Our protection is purely cosmic luck, distance and geometry.
That really underscores the power we're dealing with. I was struck by that recent example, GOB 2210009A, nicknamed the Buoy, brightest of all time.
Oh yeah, that was a monster. Even though it was incredibly distant, what, 2.4 billion light years away?
Yeah. Right. Almost halfway across the observable universe. And yet, it was still powerful enough to measurably disturb Earth's ionosphere.
It was. It briefly affected long-wave radio communications here on Earth. That just shows you the sheer energy involved, detectable effects from billions of light years away.
Okay, so let's recap the main takeaways for everyone listening. GRBs, second most energetic events known after the Big Bang.
Check. Unbelievably powerful.
The real threat isn't necessarily the instantaneous blast itself, but the long-term chemical damage to the atmosphere, specifically the ozone layer.
Right, leading to years of dangerous UV exposure. That's the killer.
And finally, because gamma rays travel at light speed, if one is aimed at us from within the danger zone, we get absolutely zero warning. Our safety depends entirely on not being targeted.
That sums it up pretty well. It's a reminder of the scale and violence the universe is capable of.
Which leaves us with this final thought, something to really chew on. The sources estimate there's roughly a 50% chance that a GRB capable of causing mass extinction did occur within about 6,500 light years of Earth, sometime in the last 500 million years.
Which means it's actually quite probable that one of the Earth's major past extinction events was triggered by one of these invisible, instantaneous cosmic blasts.
So the question that leaves us with is, if these things can happen, unseen, unpredictable, how much of the history of life on this planet, the rise and fall of species, the path of evolution, has been shaped or even dictated by these sudden, powerful cosmic events that we literally wouldn't see coming?
Makes you think about our place in the universe, doesn't it?
Yeah.
How much is driven by forces completely beyond our view or control?
Definitely something to ponder next time you look up at the seemingly peaceful night sky. That's all the time we have for this deep dive.